Hi everyone. Cool. I hope you're all having a good 44Con. Can you hear me okay? Is the mic good? Yeah? Cool. We're going to do a little talk on some of our supercomputer research. Anyone that's spoken to me in the last year or so will know that it's actually genuinely not possible to have a conversation with me without me rambling on about supercomputers. So I'm quite pleased to be able to talk about it here with people who've actually paid to come and listen to me ramble. Is there anyone who works with supercomputers in the audience? Cool. Got some people? Awesome. Now, one thing that we found in doing this research was I was genuinely expecting everything to be very, very custom. And the reality is a lot of the kit that's used is fairly familiar to most of us in this room anyway. So if you've never touched supercomputers before, don't worry, you'll get something out of the presentation. There's plenty of material here. So a little outline of what we're going to cover today. For those that have worked with supercomputers, probably you'll recognize everything up there. Those of you that haven't, it probably all looks new. Don't worry, we'll introduce you to it as we go along. And we'll start with a quick introduction. Now, I'm compressing basically 2 weeks worth of information overload that we got when we worked with supercomputers into about 10 minutes. So we won't be able to cover everything, but hopefully it will give us a good primer on supercomputers. So supercomputers or high-performance computing, I tend to interchange the words. I think no one actually agrees on a good definition of what a supercomputer is that other people agree on. So we tend to use the term high-performance computing. It kind of covers everything. But pretty much supercomputers are used when there's a need to do a huge amount of computational tasks. So things like weather forecasting. The Met Office will have a whole bunch of supercomputers that they use to forecast the weather for you. Things like data mining and cryptanalysis are great things to be doing on a supercomputer. You've got a huge amount of hardware at your disposal. Obviously, the NSA use theirs for weather forecasting, but should they want to use it for data mining or crypto stuff, they could probably switch over to that. Things like weapons simulation, so there's legislation and stuff in place now that mean you can't just go firing nukes randomly and testing them out like that. So yeah, weapon simulations are quite frequently done on supercomputers as well. And one thing I've come across lately was the SCAR project. I don't know if anyone's seen that in South Africa, the Square Kilometre Array Radio Telescope. Basically, they're going to be receiving huge amounts of data from the telescope. And the supercomputer they're planning for that is basically pretty awesome. So if you find this stuff interesting, keep an eye on that project. So, a very brief history of supercomputing. If you're anything like me, when you first heard about supercomputing or whatever, you probably thought kind of like the Cray one down in the bottom corner, really custom hardware, really custom operating system. The reality is actually quite different, and that surprised me an awful lot when we started playing with this kit. Most supercomputers are running fairly mainstream operating systems, things like Red Hat, and they're sitting on Intel architecture. And okay, a lot of the supercomputer manufacturers really bastardize their systems up a little bit. Underneath, they're basically, the vast majority are Linux systems running Intel or AMD hardware, or maybe NVIDIA stuff if they're running GPUs. But ultimately, it's fairly mainstream kit. And whilst they look pretty in this picture, the reality is they just look like any other bunch of rack-mounted servers. There's just an awful lot of them. So to throw some numbers at you, every year the top 500 supercomputers list is compiled, where people can basically brag about how fast their supercomputer is. Current top number one is Taiwan 2, which is out in China. It's a pretty awesome machine, churning out about 34 petaflops of computing power. And inside that, it's got 16,000 compute nodes. And we'll come a little bit more onto what compute nodes are in a second. But basically, each of those compute nodes has got a couple of Xeon processors in it, 3 PHY processors in it. If you've not come across PHY processors, basically, they're Intel's answer to GPUs. So you've got a large number of cores on a single chip. And I think it's around 250 odd cores. So multiply that up. 3 PHY processors, a couple of Xeon processors, you're pushing, basically you've got about 3.12 million cores in that single machine. Bundle that together with 1,500 terabytes of RAM. Storage, we're not talking gigabytes or even terabytes, we're talking petabytes. And there's 12.4 petabytes of storage in that machine. All from measly £256 million, so let's go and grab one. Basically, you get the picture. They're fairly awesome machines anyway.
Okay, so what makes a supercomputer a supercomputer? Well, there's a clock speed limit with CPUs. And basically, beyond that, everything you're looking at doing is effectively parallel computing. You've got to be able to take a task, break it up, run them in parallel. There are theoretical limits to how much of a speed up you can get, depending on the type of task. If only 50% of the task can be done in parallel, then it doesn't matter how many cores you chuck at it, the best you'll get really is a 2x speed up. But in practice, most tasks can be made very parallel, and you can approach much better speed ups. And probably something like crypto is the perfect example, as you can just split things up on the different keys you're trying, for example. You don't even really need much communication between the nodes. That's something that's particularly well suited to it. So how do you actually do this on lots of nodes? I mean, many of you are probably actually quite familiar with parallel programming, but in, say, the multi-threaded sense, running on one system. And with something like that, it's a bit simpler because though you've got lots of cores doing different things and you need synchronization between them, they all have a shared memory space that they can go to for sharing data. What changes when you start dealing with a cluster of systems is that you no longer have shared memory between all of those nodes. And effectively, what you really do in supercomputer environments is you implement the concept of distributed shared memory and you write your programs in a way that facilitate that. The main thing that achieves this is called the message passing interface in many cases. There are many implementations of it. It's a general interface, but basically it's a framework for writing your programs in such a way that you run the same program on every node, but depending on what node ID they're assigned, they will operate in a different way, and then they can share data between themselves and effectively operate as if they have shared memory between themselves, even though they may be on different nodes. And under the hood, if two of the tasks are running on the same computer, the framework should know to use RAM because that would be quickest. But if they're on different systems, then it will obviously have to involve some network transport between the two. So what really makes a true supercomputer versus just a standard cluster? Well, if you talk to some of the people in the industry, they'll probably say where you really get a true supercomputer is when you start, as well as having all the cores, all the, like large numbers of nodes, you start linking it up with extremely high performance networking kit and also disk arrays for the same speed up on disk performance. So if you imagine distributed shared memory, think how quick RAM is. If you started trying to share data that was going using, I don't know, TCP as a transport over gigabit Ethernet or something, you're dealing with something that's going to be orders of magnitude slower than what you expect from RAM. If you use some technologies that you'll find in high-performance computing environments, such as InfiniBand or MirrorNet, you can start looking at getting up to sort of 300 gigabit a second links if you aggregate several links together. And in terms of latency, you'd be looking at microsecond latency, not millisecond latency. And beyond that, if you're transferring large amounts of data, normally with TCP, the OS is involved, say, you're sending stuff back and forth, and there's a lot of slowdown involved in that. With this technology, you'll generally, basically your program will say, this area of memory now needs to be in this area of memory on another machine, go do that for me, and the network card will handle everything else using often a technique known as remote direct memory access, which sounds really bad. But yeah, it's effectively DMA, but implemented over the network. So file systems, I mentioned those before. Also, you'll have, in a similar vein, distributed file systems to enable the nodes to have a shared disk area they can access. So generally, they'll all be looking at the same data, besides maybe their boot drive. That's probably going to be unique, but in terms of anything that output from the program, they'll have a distributed file system they can all see. Common examples would be GPFS, which is proprietary. That's an IBM technology. Lustre is a very common one in use that's actually open source. In some cases, you might see things like NFS in use, but then it doesn't reach the performance levels that these will. So another thing to consider in these environments is job scheduling. So this is something that's important for OSs normally. once you move into a high-performance computing environment, you've got jobs that are being scheduled across different nodes. Suddenly, it's no longer a standard OS mechanism, and you've got to have something sitting on top of that that's probably going to be involved in the network that can handle how a job is going to be scheduled across the nodes, when which jobs run, what order they're running, what priorities they're given, and in general, users of the environment will submit their tasks and expect them to run at a certain time, and there may be rules that define when and where that happens, and that's something that will be more unique to these environments. So to give you an idea of a kind of a summary level of what the architecture of an environment like this might look like, what you're going to have is that if you've got all the nodes that you see on the right here that make up the environment, they're going to be interlinked on a high-performance network link. So that may be something custom, or like InfiniBand or MirrorNet that we spoke about before. And all the kind of supercomputer-related activities will be internal to that network. There then may be a smaller number of those nodes that are actually exposed on the corporate LAN that might be dual-home. But in general, the majority of those you'd expect to be closed on that private network, so to speak. And then basically, your scientific users of the system, for example, they may be compiling certain things on their desktops and submitting them to run via the login nodes. They may be SSHing into the login nodes and submitting commands that way. There's various ways that they can use them, but that's the kind of thing you're expecting to see. So if someone was like saying, oh, well, we've got these systems for you to look at, and you're asking, oh, what IP addresses do I look at? There's probably only going to be a small number of stuff that will be on your conventional corporate LAN. So, based on the things we've just discussed there are some important security considerations. So we've got a few things we need to think of. One, users can typically connect to login nodes, and they can run code on those login nodes and also all the compute nodes as well. Now, that's got one important implication in that local privilege escalation becomes a big deal. It's not like a web server where you've only got a few admins accessing it, and local privilege escalation maybe is only a concern if someone compromises your web server and they're looking to get further. This is a case where you potentially might have hundreds or thousands of users that are logged into these systems. So it's a much bigger deal in this environment. You've also got to understand that even though the network itself interconnecting them is private, the users have access to the inner components effectively because they can run code on these nodes, and that's an important consideration. You may have trust relationships between the nodes. Passwordless SSH is common. I know that's not something that's seen as best practice, but realistically in this environment, from a logical point of view, you should see it really as one system for the most part. It doesn't matter if someone's on root on one node or root on 16,000. Effectively, they're going to, at a logical level, have access to the same things, but you might expect to see those kind of relationships. And job scheduling, as we discussed before, is going to happen across many nodes. There's going to be network elements involved in that, and that's obviously something that's normally a critical OS mechanism that's been taken out, and now we've got something custom on top of that. That's a very important security and control that needs to be looked at. And finally, if you're dealing with a large number of nodes like that, you're going to need to rebuild them. They're going to need to be mostly identical. You're not going to have someone going around rebuilding them one by one. There's going to be some kind of imaging technology to perform this. I know that's common in many other environments. It's not something that's unique to this, but it's obviously something you're going to see in an environment like this, and it has important security contribution to the environment, so you've got to take that into account as well. So, moving on, we'll look at job schedulers first. So, basically, there are pretty much two different types of schedulers. You get resource managers. They pretty much handle actually running tasks on systems, so they'll be eventually responsible for taking your code and making it run on a node. In terms of the actual logic behind how those things are scheduled in the first place, most of them will probably have some basic functionality in there, like a first in, first out pipe or round robin or something, but they're primarily focused on actually dishing the tasks out. But you also have workload managers, and they tend to not be capable of actually running the code themselves. They're generally dependent on there being a resource manager already in place, but they'll have much more intelligence involved in how it can manage the tasks and what resources would be given out to what users and so forth. And they can even often manage multiple supercomputers, maybe with different resource managers, different technologies, and schedule tasks across multiple clusters in that way. So they sit at a high level, and we'll look at an example of one of those called Moab, first of all. So I had an environment looking at Moab. In this example, a user, if they log onto a login node, for example, they'd use a command called msub, and they use that as a way of submitting their task. So they've compiled a program in C maybe that simulates the weather or whatever it's doing. They'll then submit that job using msub, which should take care of running it on all the other nodes for them. Now, this isn't exactly what it looks like, but it kind of serves the purpose. This talks to a web server using XML. It looks something like that, which is indicating, okay, this is the code, the command I want to run on these other hosts. Run it on these nodes and run it as this, it's under this user context, and I've got an HMAC here. There's a signature to verify it. So the default behavior, if it's just out of the box, is insecure. It's, there's a key that's built into the binary that implements this, but that's obviously insecure. And if you were to leave it like that, that's a real bad case. But there are security mechanisms built in for improving it. So the more secure option that they offer themselves as their own built-in security mechanism is to use what they call authentication. Now, in this case, the key, rather than being hard-coded, is something that you can generate yourself, and then it will be stored in a root-owned file that's only readable by root. Now, what happens then is that when you call msub and you want to submit a job, you also don't know how to calculate that signature yourself. So what happens, that program itself under the hood will go and call this mauth, an mauth binary that runs as root by being a SUID binary. So that SUID binary can access the key. And basically that looks at what you've given, looks at the key, generates a signature for you, gives it back to you, and then your msub command then can submit that and get your command running on other hosts. Now, the security control in there is that it looks at the user information that's been submitted, and if it doesn't match what the caller is, so if it's looking at standard Unix ways of identifying who's called the process, then it will reject the request and say, sorry, you're not allowed to sign as that user. That's not right. So, in principle, should be secure, right? Looking into it in more detail, I noticed that, as I say, this isn't exactly how it is, but the principle of it is that there were multiple places where these were defined. So I thought, which one matters? So, looking into it a little bit further, it seems that which user IDs are looked at depends on whether you're talking to the web service or you're talking to the mauth binary. The mauth binary checks one set of credentials effectively. The web service looks at the other when determining what to run the code. So if you basically just change one to what you want it to run as and leave the other set as your own credentials, the mauth binary will check it out and go, yep, that's fine, I'll sign that for you, hand it back to you, and then you submit that to the web service, and then it will run as the other user ID you specified. Now, by default, root jobs are not allowed. So you could run code as any other user, which is obviously very valuable in the first place, but if you really wanted to get to root using this, you can still do it, because though the web service itself takes its configuration from a static configuration file, it does support dynamic reconfiguration through the same interface, and by using the exact same logic floor, you can dynamically reconfigure it to allow root jobs and then submit your jobs as root, and then you've compromised the whole environment. So that was an example of a simple logic floor we saw at the higher level in workload managers. But if I move on now, I'll pass back over to John. He'll tell you about Talk, which is a resource manager.
So yeah, Talk is a resource manager. From what I understand, it's probably one of the most widely used resource managers in the HPC world. It's based on the original PBS project. So to be honest, a lot of the code is quite old, but it's being updated, and the guy who's working on it have done a great job in version 4. It integrates quite nicely with Moab, which is what Luke talked about just now. there's two kind of key branches. The 2.5 branch is probably the most widely used. It's the one that Adaptive Computing, who maintain Talk, suggests that everyone uses. 4.2 is their latest branch. It's where they've updated a lot of the code. They've done a great job of it. I'd strongly recommend you use 4.2 over 2.5. It supports other architectures like Phi and things like that. It's not backwards compatible with 2.5, and it's multi-threaded as well, which is quite cool. So a quick kind of rough diagram of what Talk looks like. Users submit jobs to the Talk server, and the actual service that's running is called PBS server. When the job's received by PBS server, it will inform the scheduler. The scheduler will do its magic and basically tell the PBS server what to do with regards to running the job. And the PBS server will then send the job off to the compute node, which runs the PBS mom daemon, and the job will run. So reality is, put like that, it's quite simple. Underneath it's a bit more complex, but we don't need to worry about that. Now, users interact with Talk. I mean, they can do it through various different interfaces or whatever, but if they're logged onto a login node, they'll typically use commands like qstat and qsub allowing them to submit jobs. This is the qstat command, which basically the users queried the job queue. And obviously there's a bunch of information leakage there, but as you're about to see, that's probably the least of Talk's worries. So jumping back to Talk, the diagram, I was quite keen to target Talk. I know it's widely used. Looking through the internet census data, I could see that there's a fair few Talk servers exposed on the interwebs. So that made it quite interesting to me as well. So what I did, I set up an instance of Talk in my lab at home and basically configured it in the most hardened configuration I possibly could. In the PBS server, you're able to define different queues, so certain users might be able to submit to different queues and have different priorities and things like that. So I locked down all the queues so that no one was able to submit to any queues from any hosts and that kind of thing. So it was basically as hardened as it possibly could be. And then I set about trying to break it. And I shall show you a little demo now of how I managed to break Talk. So the setup we've got, basically we've got two systems here. The one with the lightish greenish background is our supercomputer, obviously named Gibson. And then we've got our attacker. You can tell it's our attacker because he's got green on black foo going on, so it's got to be an attacker. Obviously, zero cool. So I'll just show you what Talk looks like on the supercomputer. Obviously, if we're an attacker, we wouldn't have this access, but it's basically fairly standardy stuff. So Talk runs PBS server on port 15001. In older versions of Talk, it listens on both TCP and UDP ports. Later versions, they only use TCP. I've only ever really queried the TCP service. And you'll notice that the PBS server runs as root. If you think about it, it's got to submit jobs as different users, so it kind of needs to run with fairly high privileges in order to be able to do that. So if we're able to exploit this PBS server or Talk server, then hopefully we should find a nice root shell pop up for us. So we'll just grab the IP address of the Gibson. So I've bundled my exploit up into a bit of Ruby code. It wasn't the easiest exploit to write. It took a lot of ropping around to find the stuff I needed, but it's been converted into basically a pretty reliable, well, completely reliable exploit. Works every time. It will definitely work this time because it's a video. Fingers crossed anyway. So, and there you go. We've got a nice root shell on the Gibson just by firing the exploits at it. So we can do what we like. We can cat the shadow file, or we could read the garbage file if you're a hackers fan. So basically there you go. We've got unauthenticated remote root on a supercomputer, which I think is pretty cool. And also from the most unauthenticated perspective we could be. If you've seen that and you're concerned about your systems, come and have a chat. I'll tell you how to patch it.
Okay, so I mentioned I mentioned MPI earlier as being the message passing interface, being a framework of how you write programs to run in a distributed fashion. OpenMPI is an example of an open source implementation of one. There are also many commercial ones as well. That's kind of an example of it being used to run a couple of programs. I'll come back to it again in a video shortly, but basically it's something that you run. It'll push commands out to other servers and run them under your account. So for the perspective of this, you'd normally say set up key-based SSH, for example, and then it's able to log into the other host as your user. My expectation was that when you started tracing the program flow, you'd probably see it SSHs in and run something that specifies the command you're asking to be run on those other servers. What I actually saw was this. So yes, it SSHs in, but it runs a command called orted. And then there's a bunch of options passed to that. And if you see highlighted at the bottom, there's a URI given, specify a TCP channel, and an IP and port to connect to, and there's also an ID number of some sorts there. So I thought, well, that's interesting. How does it know what it's supposed to be running then? So you've got this initial secure step with SSH. So tracing the program flow and looking at network comms a bit later, and you get some binary packets going back and forth that look like this. Now I'm going to specify at this stage, you can install OpenMPI for yourself on Ubuntu or whatever you want to use, for example, as a package. This is using TCP as a transport over Ethernet. So this isn't what you probably see in many actual high-performance computing environments, but the implementation will change the transport depending on what you're using. It can support all the other bits as well. What the attack we're going to look at here may vary depending on what transport you're looking at, but this, just for your perspective here, we're looking at a standard TCP over Ethernet here. But anyway, this binary protocol, if you see the bit that I've highlighted here, you can see hello world pops up twice. Now, that's the name of the program I'd submitted. So you think, well, hang on, we've got this initial secure SSH step that's occurring, but it's not specifying in that step what program you eventually want to run. And then we've got this clear text binary protocol that's happening afterwards where it looks like it's being told later over that what command you want to run. Now, if we think back to the kind of environments this is going to be in, so obviously something like that is going to be vulnerable to a traditional man-in-the-middle attack, but is it really relevant in the environments you'd expect to see it in? Now, this is all going to be happening over the fast interconnects between the systems. That's all going to be in a data center. That's not like some large office location where if you happen to plug in your laptop somewhere, you might be able to upsweep the connection. It's not, sort of that kind of attack isn't really relevant in these environments. So the other question is, well, if you've got access to some of these systems, can you conduct the attacks from there? Well, possibly, but generally your standard kind of traffic interception attacks often need kind of raw access to a network adapter. In these cases, if you were root, for example, and had full control over everything in this case, then it's game over anyway. Like if you're at that privilege level, you've already got access to the whole system. So the point was, does it matter in this environment? Is it something that's in practice exploitable in any relevant threat context? So I wanted to know, can I exploit it as a low privilege user? That's what is of most concern to me. So if I'm a user logged onto one of these hosts or I'm submitting jobs that run on these hosts, could I exploit that, or is it just not something I'd be able to do? So I thought, well, the master node where you first submit things from, that listens on this port and it's waiting for its connectbacks. So what if I could hijack that port? Would there be a race condition? Now, if I listen on the port first, it's going to fail, and I can't barge it out of the way as a low privilege user. Once it's listening on that port, I've not got control. But once it stops, I can listen again. So I thought, well, in your legitimate workflow, it's going to start listening on this port. It's going to SSH to the other systems, run the orted command, and that's going to eventually go, okay, I need to connect back to this host, on this IP and this port. If I'm running my code on the same node that the job was submitted from, well, what happens if I connect to that port first and then talk valid MPI to it and get it to give up listening so it thinks the job's done, and then I can probably listen on that port as well. And realistically, my part doesn't involve going across the network. I'm going to do it all locally. I technically should be able to win that race if there is going to be one. So I thought, well, okay, I need to know the port to connect to. I mean, that you can probably brute force. But it turns out, looking at the binary protocol, that the ID we saw before is important as well. I'm not going to be able to easily guess that. But if on a normal Linux system, for example, you run PS, you've got the output of command line arguments applied to commands. And you can restrict that, but by default in most Linux systems you're going to see, you're going to be able to see this information. So the question I had in terms of exploitability is, well, what if I monitor the proc file system, which is where you can programmatically effectively access that data? If I'm constantly monitoring that, and then when I detect that initial SSH connection, I pull out the ID and the port to connect to, and then, quick as I can, connect to that port, talk the MPI, try and get the master node to stop listening, and then once it's down, I pop myself up there before the end compute nodes start connecting back. And then if they do connect back to me, I give them the name of a different command to run. So I was able to do that successfully, and it was actually pretty reliable. I'll just show a quick video now that demonstrates that. Okay, so first of all, we'll just see use an MPI run to submit these commands. Okay, so in this case, this is the most simple example of using it. You don't necessarily have to have an MPI-enabled application to use something like MPI run. In this case, I'm just running hostname. It redirects standard output by default, so you can run anything. In this case, I'm saying on localhost, which is the system you're looking at now, and on compute node 1, which is a remote system, run hostname for me, and then what you're seeing is the output from the two systems coming back. So moving slightly on from that, if I was to run an actual MPI-enabled application, in this case, this is simple hello world application that I wrote. The two processes will send data between one another. They basically say hello to one another, and then the output you're seeing there, depending on which line it is coming back from either localhost or the compute node, and that's the output. And so that's your kind of normal case of running something like this, what you would see. So now, switch to another tab, and just to show, I'm running as nobody in this tab. So this is on the master node where the jobs are being submitted. I'm not running as root. I'm just any old other user. And if I run a Python script that's going to basically follow the exploit process I walked through before, that's constantly monitoring the proc file system now. If I then switch to another tab, also as low priv user, and just set up a netcat listener, now the idea is that if the attack works, the command substitution should execute a shell effectively and do your standard connect back shell, and we should receive it there. So what I'll do now is just exactly the same command we did before. But now if you look, you can straight away see something's different there, because if you look at the first two lines, they've both come back saying they're running on the same master node, and that's basically a byproduct of the way we're trying to win the race and making sure that the compute node doesn't see that command occur. So in this case, that's run, and the compute node never got to connect back to that because we've won the race and now we're listening. So if you look, there's just some debugging output there, but going back to the shell, we've got to connect back with root. And if we run hostname, you can see that that's running on the compute node. And in practice, you probably wouldn't see people running jobs as root, but for any other user that's going to be submitting a job, you could apply that attack in this instance. Okay, so moving on, I'm just going to pass back to John to talk about distributed file systems.
So, as we know, everything in a supercomputer has got to be properly quick, else it's not a supercomputer. And the same is true for file systems. When we're talking supercomputer file systems, you're talking gigabit a second write speeds. I did once comment to someone who was writing to their files at maybe 700 megaseconds, and he was quite disappointed I'd highlighted that because that's very slow, apparently. I'd be quite happy with that. InfiniBand's used, or other networks like that with low latency. Obviously, you don't want things to be slow. And if you think about it, you've potentially got tens of thousands of compute nodes all hitting that same file system. So it's got to be quick. It's got to be massively parallelized. And as I said before, we're talking petabytes of storage and tens and thousands of disks. And they're all fairly standard disks. There's nothing really special about the disks. The same kind of stuff you'd chuck in any other server, really. Just lots of them parallelized up. Now, in my work with supercomputers, I've come across 3 file systems, really, that are widely used. GPFS, NFS, and Lustre. GPFS is IBM's offering. NFS, we're all security people. We've seen that before. We know its flaws. We know its other flaws. And Lustre, which is the open source offering, which, to be honest, on the face of things, looks reasonably similar to NFS to a user anyway. As I said before, performance is kind of key. So I'm not going to talk about NFS in this presentation. GPFS and Lustre is what I'm going to look at. And to be honest, I'm not going to look at GPFS in too much detail, primarily because we've not done that much work in it, because it's bloody expensive. However, well, if you follow that URL at the bottom, if you're keen to learn about GPFS, it's a really good article. But the one thing I did want to show you was the architecture that GPFS employs. So down the bottom of the diagram, you've got a whole bunch of disks. They're all set up with redundancy as well. So if a disk fails, you're not going to lose any data and stuff can continue to operate. But up the top, you've got your switch, which will be your InfiniBand switch. That will be where all your compute nodes connect into. And you'll have probably several VSD servers. But one key thing with GPFS is everything comes in through a VSD server. It'll go through multiple tiers, so you've got your remote I/O and your serial storage architecture and all that kind of stuff, but ultimately everything comes in through one route all the way down to the disks, which is quite different to the Lustre setup. So just bear that in mind. That's it for GPFS for the moment. So yeah, Lustre, it's widely used. Probably about 60% of the top 100 supercomputers use Lustre. I believe all craze these days come with some Lustre appliance bundled in it. It's resold in many different appliances. It's open source as well, so you can poke around at the code if you want. Now, the setup of Lustre looks something like this. A couple of key systems to be aware of. One is the MDS, that's the metadata server. That stores information about a file. So if you want to know if you've got permission to read or write to a file, you'll ask the metadata server. The OSS, that's basically your route into the disks. So you'll go through the OSS if you're going to read or write data to disks. So you've got kind of a separation of roles there. Now, before I poked about with this particular vulnerability, I'd not really set up Lustre. To be honest, it's a bit of a pain to set up. But reading the documentation, there was one question in my mind, which was, well, if I ask the metadata server if I can read this file and it says no, what happens if I just read it anyway? And so you thought NFS was bad. So here's a quick demo that I put together on Lustre. So this is the client machine. So mounting Lustre, it looks like a fairly standard network file server type mount. So we're mounting our Lustre volume, and we'll change into that. And I'll show you around what the setup we've got is at the moment before we actually go about exploiting it. So we've got a couple of files. I've tried to name them to kind of indicate what they are and their purpose. So everyone.txt, it's a world-readable text file. Anyone can read it. Root.txt, owned by root, and it's readable only by root. So just to let you know, we're root. If we cat the file everyone.txt, you can see its content. It's got its file name in there, just because I got slightly confused working with lots of files. I found it handy to chuck the name of the file in it. But it's readable by everyone, as the contents of the file say. If we take a look at root.txt, despite being root, we're not allowed to read that file. And the reason for that is we've got root squashing enabled. Now, root squashing on Lustre is basically the same as root squashing on NFS. So just to read the contents of that file, we'll change the root squashing permissions. Basically what's happening here is the 00 indicates the user that you're squashed to when you are root squashed. And if we're setting that as 0, you're squashed to root, which basically turns off root squashing. So having done that, we should be able to take a peek at the contents of the file. And that's the contents of the file, it's root squashed. So if we flip root squashing back on, if we set the user to be 99, which on this system is the nobody user, again, if we jump back in, we get permission denied, which is good. So if we just unmount everything and mount it all again, I'll show you how we bypass root squashing on Lustre. I'm conscious I've got to be quick because we've apparently got 5 minutes left and a lot of material to get through. Okay, so we're mounting everything exactly as we were before, same files in the same directory. Now if we jump across to a different window, I'm just going to run a bit of code that I wrote, and I'll tell you what that's going to do in a minute. So if we jump back and read the file root.txt, we're root squashed out, we can't read it. However, what that code in the background's doing is intercepting the messages between the metadata server and the client and the OSS and the client. What it's going to do is essentially find and replace the ID of the file that we want to read off the OSS. So when we next come to read everyone.txt, it's actually going to request the file root.txt off the OSS, and hopefully, all being well, we should read the contents of a root-owned file that we should be squashed out of. And then we've basically circumvented root squashing on Lustre. I'm going to bail out there now. I don't want to overhype the impact of that vulnerability. It's obviously not a great thing. But you've got to bear in mind that most places that are using Lustre, that will be contained within a supercomputer. And you know what? In order to perform this exploit, you've got to be root. And if you've got root access within inside a supercomputer, you can do far more interesting things than read files on a file system. So whilst it seems bad, it's not game over. You have to be quick.
Yeah. Okay, I'm going to try and be really quick now, but we mentioned before cluster management is important in environments like this. Tens of thousands of nodes, remote imaging is going to be the norm. We've seen a couple of different instances of this, a couple of different implementations. They both start out from your standard Pixie boot and TFTP as a first stage. But one of the implementations we saw used common protocols like rsync for doing secondary stages. The other one used its own custom protocols with multicasting and so forth. But it was a similar principle, just its own protocols for doing it and its own commands. The nature of this type of technology is that it's difficult to secure anyway. It's not unique to high-performance computing environments. There are problems with this elsewhere in general in building large networks. But it applies equally to high-performance computing environments here, and there are two things that are key you need to take into account. One, read-only images. If you leave your images on like a TFTP server or something that's got write access, someone can backdoor them, that's not good. The other thing to consider is that even if they're read-only, is not to leave sensitive information in them. Obviously sounds obvious, but you've got to work to the assumption of no confidentiality, even if the services that host these images are only on the internal part of the network to the supercomputer. Anyone who can run code on those blocks, any of your users can access them. Now the kind of things you might see in them, we've mentioned before, passwordless key-based SSH is quite common. It's sometimes required in order for certain parts of the software we've seen previously to run correctly. If root's private SSH key is put into the image, that's not good. Also, Moab key files, when we looked at Moab before, if you leave the key file for that in the image, that's not great either. You need to take these things out and make sure that added securely as a post-imaging step. So leaving root's public SSH key in authorized keys, for example, in the image is fine. And then by doing that, you can then easily push out the sensitive stuff afterwards after the build has occurred. Additionally, local privilege escalation is a big deal we mentioned previously. So though most of these are kind of Linux installs and so forth, there's custom software on there. The manufacturers have customized them in their own way. There's other surface area that's been added. So forget about patch management and your usual Unix file permission stuff. You'd look at that normally anyway. But in this case, we found that it's quite common to find additional SUID binaries, for example, that's effectively manufacturer-added attack surface. One default install we found had 2 non-standard root binaries, and one of them looked particularly interesting because it had an extract to directory option. So you can write something maybe, is that going to be a problem? The output we got was, if you ran it normally, not using the extract option, would be that it would list what was actually the contents of the local directory, but with a whole bunch of cryptic numbers before it, it looked a little bit like that. After much investigation, looking into it, it turned out that they're effectively an encoded way of representing the ownership and permissions on those files. And when you supply that same output to the extract option, it will change everything in the current local directory to match the file you gave it. Not good. So basically, you run that code on your own system, set yourself up your own bin shell that's a SUID version. You run that code to get the output with the right numbers, transfer that across to the system you want to compromise, put a shell in there, and then run it with the extract directory option and watch it change your shell to a SUID binary for you and get yourself a root shell. In the cases we saw of all these, it didn't seem like the binaries even really needed to be there. Most of them seemed to be related to the build process that didn't happen once, or that only happened in earlier stages of the imaging process and really weren't required to be there on the actual production images at all. Certainly not as a SUID binary anyway. And so if you're in these environments, you've got to make sure you look for this additional attack surface that your manufacturers are going to introduce and make sure that you remove anything you can. Okay, so I'll pass quickly back to John to summarize.
So, as you might be able to tell, there's a hell of a lot of information we wanted to get into this presentation. There's loads of stuff we couldn't cover, so we picked a good sample of different areas. Hopefully we picked some good ones that you enjoyed. But definitely in the high-performance computing world, there's a kind of big problem with security. Performance is obviously a key thing. You're not going to shell out millions of pounds on a supercomputer and then degrade the performance by using crypto for this or key exchanges for that and stuff. It's just not ideal. And there's this whole problem of authenticating users across multiple nodes securely. Now, on a single individual system, that's a far easier problem to contain. Once you've got loads of nodes all over the place, it becomes far more difficult. And there's some really good work going on at the moment by various people working on different projects. Talk is a good example. They've implemented their TRQ Auth-D, which is a nice good step up from what there was before. You've got things like Munge, which are great controls for authenticating users. So there's certainly good stuff being done. It's just perhaps they're a little bit working on their own in isolation, and perhaps they need to think about the kind of wider system rather than just their small contained component. It's definitely an interesting place to play about with stuff anyway. And I think we might have made it in time anyway. Thanks for listening. Is there any questions? Have we got time for questions? There's a few.
It's quite a short one, actually. Very interesting, thank you. Are you going to be publishing your work?
Yes, basically, we're publishing our work. Yeah, it'll all appear on our lab's website. We'll be pushing out some advisories for some of the vulnerabilities with
Great.
a bit more detail.
Thank you.
Yeah, loads of stuff.
So the POC you showed for doing the file read trick, does that work with writes?
I haven't tried it with writes. Basically, Luster's a real pain. You've got to get it all compiled into your kernel, and then prattling about's a bit of a nightmare. The best way to do it would be to modify the client, and yeah, I'm almost certain it would work with writes.
Cool.
But I haven't done it yet. Oh, interestingly, I don't know if you could change the file permissions and stuff as well as you wrote. That would be quite cool. Yeah, you've given me stuff to do when I get home. Thank you. Anything else? No? In which case, thanks for listening, guys.